Welcome to this session. This session, you're going to do an example on how to prove that a certain set is a vector space. So the problem is, show that the set of ordered n tuples of elements of any field F is a vector space over the same field F. Now, to show that any set is a vector space, we have to prove that all the 10 axioms of a vector space. So the solution for this to say let A1, A2, A3 up to AN be elements in the field F, then A1, A2, A3 up to AN, which is an element in this field F, is called an ordered n tuple. So then we can describe the set V to be the set of these elements A2, A3 up to AN, such that each AI is an element in the field F and I is a natural number. So this is a set that describes the set of n tuples. So let binary operations for addition and scalar multiplication on this set V, B, and then another thing, let us take U to be this set or this vector, V be the vector or n type of elements, V1, V2, V3 up to Vn, and W be given by W1, W2, W3 up to Wn. Let alpha and beta be two scalars in the field F, and let all these U, V, and W be n tuples in this set V that you have defined in this form. So then the first property is to test for closure. So closure with respect to addition. So if we take U plus V, we have U1, U2, U3 up to un plus v1, v2, v3 up to vn. Then on adding these two, remember these are just members of in the field F. So we'll have u1 plus v1, u2 plus v2, u3 plus v3 up to un plus vn. And you see this value is actually the same structure as the structure of any n tuple in this set of vectors, capital V. We said this is how we define the n tuple. So we have 1, 2, 3 up to n elements. Similarly, in this sum, we have 1, 2, 3 up to n elements. So this is a member of the bigger set of the bigger vector we have defined as V. So therefore, closure with respect to addition holds. So that's the first property. Second property, we have to test for commutativity. Commutativity, so it's capital M. So if we pick U plus V, because we have defined that these are vectors in the bigger set V, we'll have U1, U1, U2, U3 up to UN plus V1, V2, V3 up to Vn, and this sum will give us U1 plus V1, U2 plus V2, U3 plus V3 up to UN plus Vn. So this is how we add two vectors in this set capital V. And since these are just real numbers or elements in the field F, then we can write this one as V1 plus U1, V2 plus U2, V3 plus U3, and then Vn plus Un. Since elements in the field F obeys commutative law. Remember, the field F can be taken to be real numbers. So we always have commutativity law being obeyed by set of real numbers. So therefore, U1 plus V1 can be written as V1 plus U1, U2 plus V2, V2 plus U2, etc. Then if this result was from these two vectors, so to get this sum V1 plus U1, V2 plus V2 up to Vn plus Un, we must have had V1, V2, V3 up to Vn plus U1, U2, U3 up to Un. So this clearly is vector v, and this clearly is vector u. But remember, we started with u vector plus v vector. So u plus v has resulted into v plus u. So therefore, commutative law with respect to addition holds. So the second property. Number 3, we test associativity. So we have u plus v plus w. We had already specified that u, v, w, and vector v will be given by u1, u2, u3 up to un plus v1, v2, v3 up to vn, and then we add to w1, w2, w3 up to wn. So that's by definition of that sum. And this will be, now this one we have u1 plus v1, u2 plus v2, u3 plus v3 up to un plus vn. So this is a sum in this bracket plus w1, w2, w3 up to wn. Now, these are just members in the field F. Also, these are just members in the field F. And members in the field F also obeys associativity property. So this can be written as u1 plus v1 so this will be u1 plus v1 plus w1, comma, u2 plus v2 plus w2, u3 plus v3 plus w3 up to un plus vn plus wn. So that is what we get. The reason as to why we have done this one is because associativity holds in F. Then with this result is the same thing as saying u1, u2, u3 up to un plus v1 plus w1, v2 plus w2, v3 plus w3 up to vn plus wn. If you see how this result was obtained from this step, similarly, this is to get this result, we must have done this sum. Now, this will be u1, u2, u3 up to un plus, in this square bracket, it's like I have added vector v, then plus w. So we'll have v1, v2, v3 up to Vn plus W1, W2, W3 up to Wn. Now clearly, this is vector u, and here we have this vector v, and this other one is vector w. And remember, we started with saying that into brackets u plus v, close brackets plus w. So this was u plus v plus w. So you see, this one shows that associativity holds. So therefore, associativity with respect to addition holds in V. So that's the third property. Number 4 is what we call additive identity. So since the element 0 can be found in our field F, then the additive identity in this set V, capital V, is, we have this 0, 0, 0. So we have n zeros. Since if you say u plus this vector we are claiming to be our additive identity, we'll have u1, u2, u3 up to un plus 0, 0, 0 up to the nth 0. And then with the usual addition of these two vectors, we have u1 plus 0, u2 plus 0, u3 plus 0, up to un plus 0. And you see, this 0 is just the normal zeros, like 0, the real number 0. So any number plus 0 will give you that same number. So this is the same as u1, u2, u3, up to un. So this defines vector u, and so we are saying that u plus this 0 vector gives us u. So therefore, additive identity in this bigger set V exists. Number 5, additive inverse. Does additive inverse exist for this set V? Now, given that vector u is u1, u2, u3, up to un, then this vector is in the bigger set V. Negative u is negative u1, negative u2, negative u3, up to negative un is also in this bigger set V. So that if I pick u plus negative u, I'll have U1, U2, U3, up to UN, plus negative U1, negative U2, negative U3, up to negative UN. And this we add U1 plus minus U1, U2 plus minus U2, U3 plus minus U3, UN plus minus UN. Now, since these are just real numbers in this field F, then this is the same thing as writing U1 plus minus is minus U1, U2 minus U2, U3 minus U3, up to UN minus UN. And this will give you 0, this will give you 0, this will give you 0, up to the end 0. And you see this is the 0 vector that we have defined in case 4. So U plus minus U is resulting into the identity, additive identity, which is given by 0. So therefore, additive inverse in V exists. And then number 6. So it said that let the constants in the set V be given by alpha and beta. So for us to prove closure with respect to scalar multiplication, we have to show that if we pick alpha in the field, then when you multiply by any vector in V, we'll still get a vector in V. So given an alpha in the field F and vector U, which is U1, U2, U3 up to UN, in this set capital V, then alpha U will be alpha U1, U2, U3 up to UN, which is the same as alpha U1, alpha U2, alpha U3, and then alpha UN. And clearly, you can see that this is a vector in this set V because it has n elements as all vectors defined in V have n elements. So this is an element in V. So therefore, closure with respect to scalar multiplication holds. Number 7, if we take alpha, so this actually is called the left distributivity of multiplication with respect to addition. So left distributivity with respect to scalar multiplication over addition in our set capital V. So does this property hold? So this means that if we have alpha and we have two vectors u and v, let's see what we get. We'll have alpha. By definition, u is u1, u2, u3 up to un plus v1, v2, v3 up to vn. And when we add this, we'll have alpha u1 plus v1, u2 plus v2, u3 plus v3 up to un plus vn. And you see this is a scalar, so we just multiply every term here. So we'll have alpha u1 plus alpha v1, alpha u2 plus alpha v2, alpha u3 plus alpha v3, all the way up to alpha un plus alpha vn. So that's just how we multiply a scalar by a vector. That scalar multiplies every element of the vector. This is the same as, now you see every sum here has starting with alpha u1, alpha ui. So for us to get this result, we must have added alpha u1, alpha u2, alpha u3, up to alpha un plus alpha v1, alpha v2, alpha v3, up to alpha vn. And you see every element here has alpha, so we can factor it out. So write alpha u1, u2, u3, up to un. Here we have also factor out alpha, alpha v1, v2, v3 up to vn. So this is giving us, this is the answer for alpha u plus v. But you see, this is the definition of u vector, and this definition of v vector. So we have successfully shown that if we take alpha multiplied by the sum of the two vectors u and v, then it's the same as the sum of the sum of alpha multiply each of the two vectors. So therefore, distributivity property holds. So that is left distributivity. We also have right distributivity. Number 8, right distributivity. Now, for right distributivity, we'll have alpha plus beta, and then we multiply by the vector u. So this is the same as alpha plus beta, and then u1, u2, u3, all the way up to un. So this will be alpha plus beta, you multiply by u1, alpha plus beta, you multiply by U2 alpha plus beta, you multiply by U3 all the way up to alpha plus beta multiplied by UN. I remember alpha, beta, and UIs are elements in the field F. So since elements in the field F obeys distributive law, then this is the same as alpha U1 plus beta U1, alpha U2 plus beta U2, alpha U3 plus alpha plus beta U3, all the way up to alpha UN plus beta UN. Now you see in this new vector, we have alpha UIs at the starting elements of each sum. So that tells us that for us to have gotten this answer, then we must have had alpha U1, alpha U2, alpha U3, up to alpha UN added to beta U1, beta U2, beta U3, up to beta UN. So remember, this is alpha plus beta, then multiplied by U vector. Now this, you see alpha is multiplying every element here. So we must have had alpha multiplying U1, U2, U3 up to UN. Here also beta is common, so factor it out. U1, U2, U3 up to UN. Don't forget that this is the result for alpha plus beta times the vector U. This is the definition of U, this is the definition of U. So this tells us that alpha plus beta times U is nothing but alpha U plus beta U. And you see this clearly shows that distributive property holds. If you want to be more specific, you say write distributive property of addition with respect to scalar addition holds. And then number 9, the last one, the second last one, associativity with respect to scalar multiplication So we have two scalars, alpha and beta, defined in F from the start. If we multiply by a vector U, then you'll have alpha beta. Vector U is U1, U2, U3, up to UN. These are scalar, these are vectors. So this scalar multiplies every vector. So this is the same as alpha beta, U1, alpha beta, U2, alpha beta, U3, up to alpha beta, UN. That's the definition of multiplying a scalar by a vector. So the scalar multiplies every element of the vector. But you see, this, you can write it as alpha, beta, U1, alpha, beta, U2, alpha, beta, U3 up to alpha, beta, UN. What is allowing us to do this one is because alpha, beta, and UIs are elements in the field F which obey associativity. So that's why this, we can switch the brackets this way here. Now with that one, you see every element here has an alpha outside. So we can say that's the same thing as saying alpha, beta, U1, beta, U2, beta, U3, up to beta, UN. So this is alpha, beta times U. So remember, this can be written as alpha, and then I factor out beta because it's on every element in this vector. So alpha, so beta into U1, U2, U3, up to UN. But you see, this is the same as saying alpha into beta, but this defines vector U. So we have successfully shown that alpha, beta, if you multiply by U, is the same as alpha multiplying by beta U. So therefore, associativity with respect to scalar multiplication holds. And then lastly, number 10, identity multiplication. So they exist an element 1, which is in the field F, such that if I say 1 times U, the same as 1 times U1, U2, U3, U4 up to UN, and this being a scalar is the same thing as saying 1 times U1, 1 times U2, 1 times U3, up to 1 times UN. Remember, 1 is just a real number, UIs are real numbers. So 1 times any number, you get the same number. So 1, U1, this is U2, this will be U3, up to UN. And this not really that directly, this is the definition of the vector U. So i.e., 1 times U vector, you get U. So therefore, because all the properties identity multiplication exists, and since all the 10 axioms of a vector space are satisfied, then V is a vector space. Remember, V was the set of all n tuples of elements picked from a field F. So that's the solution. Thank you.